welcome back. Thanks for being here, and we're very happy this morning to have a session on optimization. And the first talk will be given by Eddie on QAOA and what we do with it. So thanks, Eddie.
Yeah, okay. Can everyone hear me okay? All right, so, well, I'm going to talk about two results, which I think are interesting. So I want to review a couple of facts about the QAOA, which I'm doing because it's going to help my presentation. So let's start with that. So what we're interested in here is combinatorial optimization. So we have situations where you have n bits and m clauses. And typically we have a cost function, C of z, which is a sum over clauses. We have m clauses. And each of these little clause functions, it's a 1 if the clause is satisfied, and it's 0 if it is not. So this is the general framework for combinatorial optimization. I know people know this, but I'm just trying to get language down. So, but the goal in combinatorial optimization is to make that, to find the maximum of that function. And of course, that's the mother of all NP-complete problems. So that's a very ambitious goal, to find the efficient algorithm for that. So what we're going to be interested in is something a little less ambitious, which is finding a good approximation. So that means we want to have an algorithm that outputs a string such that C of z over C max is big. And we'll have to talk about what that means. And that's called approximate optimization. And please interrupt me, because this is, you know, if you understand something. So the quantum algorithm, which we're going to use here, it has two basic ingredients. It's an alternation of unitary operations. The first unitary, which I'm going to define, depends on the cost function. And it's the exponential, depending on a parameter gamma, of the cost function. And note that since the cost function is the sum of commuting terms, this can be written as a product of over the clauses of e to the minus I gamma c, e to the minus I gamma c sub alpha. Now the other operator, now that doesn't change the bit strings, it just puts phases on them. So we have another operator which actually moves the bits around, like sometimes we call it like the driver. So consider B, which is the sum of the sigma x's, and then the unitary, which we have here, is the exponential of this. And that's just a rotation around the x direction by an angle beta of all the qubits. And typically, but not always, we start in the uniform superposition over all strings. And note that these are all easy to construct operators. And you can imagine putting this on hardware. Now, for any integer p has become for us the definition, sort of the depth of the algorithm. I want to define two p parameters. So there are p gammas and p betas. And then we're going to make a state, which is start with the initial state, then act with this operator that depends on the cost function with angle gamma 1. They're angles because things are all integer valued. So the cost function is integer valued, and the sigma x's have integer eigenvalues. So it's enough to think of these as angles. And then we apply the B operator. Then we have this alternation. So there are a total of 2p applications of these unitaries. The circuit depth is at most mp plus p. That's not so important because we're not really worrying about implementation here. But now what we want to do is we want to make this quantum state, which depends on 2p parameters, and attempt to make the cost function big. So the goal is to make the cost function big in the quantum state. So we define this fp that depends on the depth of gamma and beta as this function, and mp is the maximum over it. It's easy to see that the maximum can only increase as you increase the depth, because if you go up in p, you're doing a relaxed optimization relative to the previous level. So this can only increase, and actually can show that as p goes to infinity, the limit of mp is c max. But that's not particularly useful to me, because this really requires p to grow like exponentially in n. And I'm not really interested in that. It's just a math fact of not great relevance that you can get to the infinite value. Now, the quantum algorithm with angle search, one of the ways you might approach this is to start with fixed angles, gamma and beta, use the quantum computer to make the state, measure to get a string z, and compute C of Z, repeat with same angles to get a good estimate of the previous object, and then repeat with new angles to try to go uphill. Now, that's what people talk about when they talk about variational quantum algorithms, where you use the quantum computer to make calls to a function, but you have some kind of outer loop that you use to go up. And so we might imagine running the QAOA in this mode, or we might not. Depends on what we want to do. But for fixed P, we can actually classically pre-process and determine the best angles in advance. And I want to give you the argument for that. Let's look at max cut on 3 regular graphs. So max cut is, I think we all know what it is. The cost function for max cut, if you have an edge jk, is a half minus ejzk. You see, this thing is a 0 if these two things agree, but it's a 1. In other words, it's happy if they disagree. That's the cost function for max cut. And if you look at p equals 1, let's look at the contribution from one edge. So this is, I'm on a 3 regular graph. I have an edge jk. So since the cost function is a sum, if I look at what I get, I have the expectation in the state S of this thing with jk. This is just what it is at the lowest dimension. And S is the product, is a product state because it's a product of eigenstates in the x, of spins pointing in the x direction. Now, let's look at the innermost conjugation where we conjugate jk by the betas, b's. Well, that just rotates the qubits, but it doesn't change the locality. But now, when I conjugate by e to the I gamma c, in other words, this little piece here, that pushes the operator that's in the middle here beyond the 2 qubits I'm looking at. But the only thing it can involve are the bits connected to j and k in the graph. That's all you see. So you have this edge, and then you can see the things in the graph. But since I'm looking at a 3 regular graph, there are only 3 subgraph possibilities. The sort of obvious one is j is connected to 2 friends, k is connected to 2 friends, and none of these are friends of these. But the other possibility is I have 1 triangle or 2 triangles. But there are really only 3 possibilities. And what that means is that each subgraph type gives a special function of gamma and beta, which does not depend on n or m. And that means that these can be evaluated on a classical computer looking at 4, 5, or 6 qubit subsystems, because this is 6, 5, 4 qubits. And given that, if I know the number of subgraph types in the graph, which I can count, then I can evaluate this function and optimize it. And using this, we were able to show if p equals 1, the QAOA will produce a cut that is at least 0.6924 times the optimal cut. And that we could prove for all instances of 3 regular max cut. So the thing that we accomplished there was we got a worst case performance guarantee by analyzing the algorithm. Okay, are we comfy? So now I want to change it and now not look at a worst case performance, but look at the QAOA on typical graphs. So I want to imagine that I'm generating graphs by some distribution. So for example, I might be sampling uniformly 3 regular graphs. Or I might include each edge with a probability 3 over n minus 1. If you do that, the average degree is 3. Or I might include each edge with a probability d over n minus 1. That means the average degree is d. Whatever, I have a distribution. And I'm not looking at worst case, but I'm looking at typical. Now, what we're going to demonstrate now is that if you look at the expected value of the cost function in the state gamma beta, that for typical instances, this function is the same for all the instances. So this thing concentrates. And that's sort of interesting. Up to corrections, this is, I wrote a paper on this with Fernando, Michael, Sam, and Hartmut. And let me argue why that is the case, this concentration. It's very useful to know this. Consider p equals 1. Let's go back to my max cut example. Let's imagine I've uniformly generated them in some manner. So for large N, the fraction of subgraph types will concentrate. Because if I have a giant graph and I count the number of each subgraph type, it's going to be a fixed fraction because the graph is giant and I've distributed it uniformly. In fact, it's all going to be these because if you have a giant graph, it doesn't have little triangles. But it doesn't matter. In principle, just it's these three types. But since I know the subgraph types, this is instance independent. Okay, so that just proved that for, p equals 1 on 3 regular graphs, it concentrates. It's the same for every big 3 regular graph that I generated. Okay? Now, what? Yeah.
Can I ask a question?
Sure.
What do you mean by uniformly generated?
Well, I mean that, let's say,
Over all 3 regular?
yeah, let's say that is an ensemble, right. I could have an ensemble of all 3 regular graphs. I pick each one with equal probability. That's an example, yeah. Mm-hmm. That's a well-defined ensemble.
Sure.
Yeah. Okay, so now, so we just proved the concentration, and you see this proof will generalize to a higher p as long as p is small enough that I have subgraphs which I can analyze, which are not covering the whole graph. So this just proved concentration for small p. Are we comfy with that? I mean, this will work if p is 2, 3, 4. It didn't just have bigger subgraph types. Okay, but now I want to show you something that's interesting, which we discovered numerically, which is I'm going to look at 20 vertex, 3 regular graphs. So 3 regular graph with 20 vertex has 30 edges. And at each of them, I look at 25 samples. But then what I do is we go to p, let's say p equals 3. And let me just normalize this for you. If you have a graph with 30 edges, the typical cut will be 15. That's just the way it works out. It's half of 30. So 15 is kind of the number to think about as what you would get randomly. But I can choose the parameters so that I'm getting a low value of the cost function. And what we find is that if I go to p equals 4, and I find some fairly low value, because this is like 3.9, and we toss 25 samples, the standard deviation is this. It really does concentrate. In other words, I've chosen the angles to make the cost function small, and it concentrates over the samples. And if I pick random angles, well, then everything is near 15. And if I pick good angles, meaning high values, these only improve as you increase the depth. I also find concentration. So this is showing numerically that it works. But note what happens here with p equals 7. You see, if I have a subgraph if I'm on a 3 regular graph and I have a subgraph with the little tree I showed you had 6 things coming out, 6 nodes. But if I go to p equals 2, my next graph, the size of it is 14. And if I go to p equals 3, the next size is 30. And if I go to p equals 4, it's 62. So by the time I'm at p equals 4, my subgraphs are covering the whole graph. So this is already big P for the size I'm working at. And so by the time I'm at 7, I've multiple covered the graph. So there are no subgraphs anymore. So the subgraph argument went away, but the result is still there. So that's sort of interesting. Okay, because I lost my argument, but I still have the same result. So why can that be? Well, consider f gamma beta. It's a sum over clauses. And imagine that there is a distribution over instances. And think of C alpha as a random variable. Now, if these are independent, then the sum will concentrate by the law of large numbers. It doesn't depend on n or anything. It just depends on the number of samples, right? If you want to estimate, if you have a big jar with 1 trillion jelly beans and you want to estimate the number of red ones, it only depends on the number of samples. It doesn't depend on how many things are in the jar. And so here, if these are independent, then this will concentrate by the law of Nod's numbers. Does that make sense? So now the question is, do they look independent? And so we tested that. We actually went to the computer and measured correlation coefficients between different C alpha and random instances. And they were always very small, the correlation coefficients. To a statistician, the value 0.04 is tiny for correlations. They think of big correlations when that number is close to 1. So they're uncorrelated. So we don't have a proof that this works for large P, but the numerics suggest that our intuition is correct, and that if you go to higher bit number, it's hard to believe the correlations will increase. So anyway, that's the statement. But this has certain, why is it doing that? Okay, come on, computer. Oh no, what am I doing? I'm so sorry. Where's my
Slide on, it's on the other screen.
It's on the other screen? Oh, there it is. It just has a funny color. Okay, who cares, right? All right, so a new strategy for random instances. So what you could do is pick one instance and work hard to get good angles. And maybe that requires many calls to the quantum computer, but then you can use these angles for other instances. So it gets rid of the outer loop, because it says once you've found good angles for one instance, you can use them for all of them. And that's very helpful in terms of your approach to this. And this works, because you saw my numerics. Does that make sense? Once you know that the parameters for one instance, the best parameters are the same for the next instance, then you don't have to search again. And of course, it doesn't produce the string. You still need the quantum computer to make the string. Go ahead.
Are the good angles unique, or there are multiple good angles?
Typically, this landscape is not that gnarly. It just has, one local minimum. I usually, numerically, I search for the global minimum. It's just one global minimum. Or maximum, excuse me, with respect to the angles. Yeah.
You said you could use the same angles for like the 3 local graphs, like an ensemble of that. Do you know if that holds for any ensemble of graphs? Or like
Well, I think my argument is just didn't care about, my argument is for any distribution on any kind of sets of graphs. Yeah, I think these arguments are way more general than the particulars that I've outlined. There's nothing to do with that. So that's kind of, okay. So now, well, I want to go to my next thing, Sherrington-Kirkpatrick. But another finding we had is that if you toss a random graph at 10 bits at p equals 8 and you get good angles, then, if you do it numerically at 10 bits, p equals 8, you get a very good approximation ratio, 0.984. But you can use those same 16 angles at 24 bits, and you get also a very good approximation ratio. So it also says that if you find good angles on a random graph at low n, and then you can use that at a high n, and it still works, which is very helpful. But I don't know why that's the case at high p. At low p, it's obvious, but at high p, I don't have an argument for why that works, but I just know it does. Okay, so maybe I'll skip this, but this can result in all kinds of nice strategies for running the QAOA in which you don't have to do outer loop optimization. Okay. So now, are there any questions about that? Because I'm going to change the topic. Yes.
So with the angles, I thought that as you increase P, you had more angles.
Yes.
So if I do it at P equals 10, I come up with the angles, and then I go to P equals 20.
No, I didn't say P equals 20. I said, I'm sorry, go ahead.
So what am I doing for those extra angles? Am I keeping P fixed?
No, if I said going to higher P, I meant to say higher N.
Oh, thank
I misspoke then, if I said that, yeah. Maybe I misspoke, yes. No, that's fine, it's probably me. So, I was at P equals, I think I was at P equals 8, and I went from 10 to 24, okay? I kept the same angles, yeah.
I don't know this for Maxcup, but I know for traveling salesmen, a lot of the hardest optimization instances are like relatively specifically picked. Like they have like specific types of loops and things like that. So this applies to random angles. You thought about like if you were to pick one of these like hard instances?
No, this is not for worst case, no. But No, I mean, I'm just talking about typical cases. I don't have a worst case result. Yeah.
Going back to the previous question, like if you increase n, doesn't the number of angles increase as well?
No, because that's determined by P, the depth of the circuit.
Oh, you're
No, the circuit depth is the same. No. Okay? Yeah, okay.
So considering there are some similarities between QAOA and adiabatic quantum computation, we might expect that these angles follow some kind of adiabatic schedule. Do you observe?
So yes, I do observe that sometimes, but you know, it's very hard if you're at p equals 2 and n is gigantic to think of it as an adiabatic algorithm. But it is a fact, and I will talk about this more in the Sherrington-Kirkpatrick, that very often you do see, if you plot the angles, that the betas are decreasing and the gammas are increasing. Kind of looks adiabatic-ish. Yes, okay, go ahead.
So have you looked at so you said if you fix the values, you get, you know, as you increase the size of your graph, you fix the angles, it still works. Have you, I mean, compared that to just directly optimizing on these larger graphs?
Well, no, but then, no, but when I go to the larger graph, I can use that as the starting point for further optimization. So that's what I didn't get into the strategies for running the computer. But no, but suppose I tell you I can get good angles at, you know, 10, I have p equals 8, there are 16 angles. I get some good angles at 10 bits. Then I go to 24, and I just showed you the value using those angles, but that can be improved because that could be the start of a local search on the angles.
So that would be an estimate of how optimal that.
I don't have that.
Okay.
No, because I can't show that that's true. It's very hard for me to estimate something I can't show is true. Yeah, I can't show it's true, I just know it's true, so puts me in a tougher position. Okay? I'm going to go a couple minutes over because I think I have a whole other topic, but I'll try to do it fast, okay?
Yep.
Are we good? All right. I guess you're not going to say no, okay? Yeah, thank you, because, yeah, the Dutchman would take my head off. All right, so I would like to change the topic, and we're going to talk about a very fascinating model. It's called the Sherrington-Kirkpatrick model. This model was introduced in the 70s, and the way it works is you have n bits, and the variables are now ZAs, which take the value plus or minus 1, and I have a cost function. This is a complete graph. So it's 1 over root n, the sum on a less than b, JAB, ZA, ZB, with the only thing I really care about is that the mean of JAB is 0 and the variance of JAB is 1. It can be any distribution with that property. And this thing is called the Sherrington-Kirkpatrick model, and it was developed in the 70s, and actually I believe simulated annealing was designed to work on this particular model. But as n goes to infinity, you can show that the maximum of C divided by n is 0.763 ... Now, this is a famous result due to Giorgio Parisi in the 70s, which introduced all these concepts like replica symmetry breaking. But if you actually look at what he did, it looks like voodoo. I mean, it's really strange math, and no one could understand it. But then this French mathematician Talleyrand proved it was all rigorously correct. And so this is like the prototypical spin glass model where we know what the best configuration is. All right? And there's the whole world centered around this. So that's why it's a good thing to look at. Okay, and this is calculated to 14 decimals.
So do you know the configuration or do you know the energy?
No, it just tells you the energy. It doesn't give you the configuration. What I'm after now is finding configurations. Exactly. It tells you the energy, not the configuration. Right. So now I want to look at the p equals 1 QAOA. And here, what I'm going to do is this is what it looks like. I want the cost function over n because the way I've normalized things, the energy scales with n. So here, I'm going to, in this thing, I'm going to insert complete sets, a complete set of Z1, Z2, Z3. So this is C of Z1. This is the matrix element between Z1 and Z2, C of Z2, et cetera. So I'm just writing it out. But C of Z is 1 over root n, the sum of A less than B of J, B, Z, A, B. But you know, if phi is small, then the expected value of j of e to the I phi j is 1 minus phi squared over 2, and the expected value of j of e to the I phi j j is I phi. That just comes from the fact that the mean is 0 and the variance is 1, and phi is small. But my phi is going to be small because I'm going to average over the j's, but I have a 1 over root n in front because of the way I set it up. So I have a small phi, and that is going to allow me to actually average over the j's. Now, the reason I'm keen on this, so let me tell you the result, and then I'll say why I like it, is because upstairs I have this with JAB. Downstairs I have this, and I can just use the fact that I know how to average to do the averaging. I average over instances. And then if I average over instances, in other terms, take the expected value over j of gamma beta c over n gamma beta and take the limit as n goes to infinity, I get this formula. So we can calculate it as n goes to infinity by hand. This is just calculated. And then you can optimize it. And at gamma equals a half and beta equals pi over h, you get 0.303, which is, you know, halfway to Parisi almost. Now, the reason that this is a little, which I'm very pleased with this, is because, you see, if you look at the Parisi thing, usually what people do is they, you know, they want to find, they have a cost function, so they look at e to the minus beta times the cost function, and they want to take beta to be small, and they take, you know, the trace of this. And what you might attempt to do is, this depends on configurations j, so you might want to take the expected value with respect to j. That gives the wrong answer. That's what Sherrington-Kirkpatrick did. What you have to do is first take the log, and then take the expected value. And that's what makes this, that's what's hard. This is getting the order of the log and the averaging right. And so, so the whole point of Parisi is he figured out how to take the expected value of the log. But I don't take a log. I just do it directly, and that's what allows me to proceed. So anyway, we could do that. And then beyond that, we can, for any fixed p, we have an iterative procedure to evaluate the limit as n goes to infinity of this quantity. We actually can do this for any p. But the procedure we have involves a numerical evaluation, and it gets, and the time for the numerical evaluation goes to like 16 to the p. But we were able to carry it out to p equals 8, and we got up to 0.607. So we keep doing better and better. So this is, I mean, we have, I think it's a nice result because we can show that as n goes to infinity, I can guarantee you this performance for very shallow depth. P is not growing with n. It's, you know, 8. And I'm getting, as n goes to infinity, a nice result. Not only that, but we can prove the next thing, which is concentration. In other words, we can prove that as the limit as n goes to infinity, the expected value of the square is the square of the expected value. And what that means is that that proves landscape independence, because that proves, this is for over different instances. This proves that this says that the variance over instances of the expected value of the cost function is going to 0 as n goes to infinity. So that means that we proved for this model the landscape independence that I was referring to before as n goes to infinity. But I can also show something else, that as n goes to infinity, for a typical instance, every string you measure will have that value as well. So it concentrates both over the instances, and then it concentrates over the measurements. Okay, which is, it's sort of nice to know that. So I mean, this is really what I want to show, and I'm working quite hard on it and failing. I want to show that for n goes to infinity and then p goes to infinity, we achieve the Parisi value. We haven't done that yet. We just see it getting better. but it's technically complicated to show that. I haven't been able to. We're working on it. And then, I mean, now though, we want to apply these, you see, this idea of tossing random instances and analyzing the QAOA by averaging is a new tool that allows us to get formulas that were inaccessible when we were talking about worst case instances. So, I mean, I would like to apply our techniques to other problems where instances are drawn from whatever distribution. I don't know. I mean, I tend to look at, like, I'm looking now at independent set on 3 regular graphs. Oh, that's the end of my talk. Okay, perfect. Thank you. Okay, any more questions?
One quick question, and after the 3 talks there will be a break, and then all the speakers will be back for a discussion session, so we'll have more time for questions.
Yeah.
But a quick one.
So the results you have here are for n equals infinity, where you just take and repeat the limit, I assume.
Yeah.
If you do this practically, how large should n be in order to see these effects?
I'm not sure. I think if n is in the 20s or 30s, you'll see. No, wait a second. I'm trying to remember. No, inside my paper, we show results for n of 26. And it all works very well. And then,
Is the deviation then from n equals infinity, do you know how it scales? The 1 over n direction.
no, actually, that's I wish I knew that, because if I knew exactly that, I would be able to prove that I hit the Parisi value. So that's what in fact, all I really need to prove is that it's monotone in n. I can't prove that. If I can prove it's monotone in n, I will be able to prove we go to the Parisi value. So I don't have complete control over finite n effects. I don't. Except at p equals 1, where, p equals 1, I can analyze everything. We have the exact formulas for all n. But beyond that, I think we also have the exact formulas, I think, for p equals 2. But, for big P, I don't have the 1 over n corrections. That answers your question. I'm trying. I want them.
Okay, so let's thank Eddie again.
Okay, thank you.